Intermolecular forces are attractive forces between molecules. They are the forces that hold separate molecules together. Intramolecular forces are the forces that hold atoms together in a molecule. What is the difference in the strength between intermolecular and intramolecular forces of attraction? It takes 41 kilojoules to vaporize 1 mole of water. In other words, it takes 41 kilojoules to break the intermolecular forces of attraction between a mole of water in the liquid phase. It takes 930 kilojoules to break all the oxygen-hydrogen covalent bonds in a mole of water. It takes 20 times the amount of energy to break the intramolecular forces of attraction in water compared to breaking the intermolecular forces of attraction in water. Generally speaking, intermolecular forces are much weaker than intramolecular forces. There are certain things that are a measure of the strength of intermolecular forces of attraction. Boiling point, melting point, heat of vaporization, heat of fusion. The higher the boiling point, the stronger the intermolecular force of attraction. The higher the melting point, the higher the intermolecular force of attraction. The larger the heat of vaporization and heat of fusion, the higher, the stronger the intermolecular force of attraction. Consider a glass of water. Why do the molecules of water stay together? There must be some attractive forces between the molecules. Consider these 3 molecules of water. It is the intramolecular forces that hold the oxygen and hydrogen atoms together. These intramolecular forces occur between atoms and are very strong. But what is it that holds the molecules of water together? Intermolecular forces occur between molecules. They are much weaker. There are 3 types of intermolecular forces of attraction, and the kind that molecules experience depends on the type of intramolecular bonding in a molecule and its shape of molecule determine the type of intermolecular force. The type of bonding and the shape of the molecule will determine the type of IMF that molecule experiences. Intermolecular forces of attraction, or IMFs, are also known as van der Waals forces of attraction. There are 3 types of van der Waals, 3 types of intermolecular forces of attraction. London dispersion forces are the weakest. Dipole-dipole attraction. And hydrogen bonding, which is the strongest of the IMF. Let's look at each one individually. London dispersion forces are experienced by all atoms and molecules. However, London dispersion forces are the only IMF experienced by nonpolar molecules and the atoms of the noble gases. London dispersion forces are caused by the random motion of electrons. Consider the two nonpolar substances below. Notice that there is an equal distribution of electrons in these nonpolar substances. Since electrons move randomly around the nucleus, at any instant, the electron distribution in an atom or molecule can become asymmetrical, creating an instantaneous dipole, which is also referred to as a momentary or temporary dipole. Consider the diagram below. Notice that the electrons in both substances is concentrated on the right side. This creates a partial negative charge on the right side of the substance and a partial positive charge on the left side of the substance. This is momentary or a temporary dipole, but is enough to cause an intermolecular force of attraction between the opposite ends of these momentary dipoles. Like all IMF, London dispersion forces result from the attraction between opposite charges. The strength of the London forces increases with the size of the atom or molecule. That's because larger atoms or molecules have more electrons to become polarized or unevenly distributed. This increases the strength of these momentary charges, increasing the strength of attraction. The larger the atom or the larger the molecule, the stronger the London dispersion forces of attraction are. Consider the boiling point of four noble gases: helium, neon, argon, and krypton. Remember, as you go down a family, atomic number increases, which means you have more protons and more electrons going into higher energy levels. Smaller, lighter atoms or molecules have less electrons and are less polarizable. Therefore, they experience weaker dispersion forces. This is evident in the increased boiling point of the noble gases. Since the electron cloud in krypton is larger and more polarizable, it has a stronger intermolecular force of attraction as London dispersion forces. Therefore, krypton has a higher boiling point than helium, which is the smallest. As the size of the molecule or atom increases, the strength of the London dispersion forces increases and boiling point increases. Now consider the halogens: fluorine, chlorine, bromine, and iodine. All are diatomic elements held together by nonpolar covalent bonds. As the molecular size increases, the number of electrons increases, and the potential for being polarized increases, resulting in stronger London dispersion forces of attraction. Because the fluorine molecule is the smallest, its London dispersion forces are the weakest, and it has the lowest melting point and boiling point temperatures. The iodine molecule, which is the largest with the strongest London dispersion forces, results in iodine having the highest melting point and boiling point temperatures of the halogens. It's also important to consider the effect of London dispersion forces and the physical state of each of the halogens. Fluorine and chlorine are relatively small have the weakest London dispersion forces of attraction. Both fluorine and chlorine are gases. Bromine, which is slightly larger, has stronger London dispersion forces of attraction. Bromine is a liquid. Iodine, the largest of the four, is the biggest with the most electrons, the most polarizable. It has the strongest London dispersion forces of attraction. Iodine is a solid. Dipole-dipole attraction. Dipole-dipole attraction is the attraction between polar molecules. It is when the positive end of one molecule is attracted to the negative end of an adjacent molecule. Dipole-dipole attraction is slightly stronger than London dispersion forces. And the more polar the molecule, that means the greater the difference in electronegativity, the stronger the dipole-dipole force of attraction. The last type of intermolecular force of attraction is hydrogen bonding. It is a special type of dipole-dipole attraction. It is the strongest of all intermolecular forces of attraction. Hydrogen bonding is important for molecules that contain HF, HO, or HN bonding. Fluorine, oxygen, and nitrogen are very electronegative, so when bonded with hydrogen, it forms a very strong dipole. The partial positively charged hydrogen is attracted to the lone pair of electrons in the molecule next to it. Let's consider the effect of hydrogen bonding on boiling point. We are going to go down group 16 and look at the boiling points of the molecules H2TE, hydrogen telluride, hydrogen selenide. It should make sense to you that the boiling point is decreasing as the size of the molecule decreases. Hydrogen sulfide, even smaller, with an even lower boiling point. You would expect that hydrogen oxide would have a boiling point that follows the line. Remember, if only London dispersion forces of attraction were present. The strength of the IMF is directly related to the size of the molecule. And since H2O would be the smallest molecule, it should have the weakest London dispersion forces of attraction, meaning water should have the lowest boiling point. But what do you know? Water has a boiling point of 100 degrees. That is because water has strong hydrogen bonding. If it weren't for hydrogen bonding, at ordinary temperatures, water would be a gas. Because of hydrogen bonding, because of the strength of attraction between the water molecules, water has an extremely high boiling point. It does not follow the trend of the molecules in its family.